Okay. So, hey everyone, we're Woven Wind. I'm Katie, this is Miles, Maggie, and Kevin. And right now we are doing an Allen Elementary project, and we are in Gate 2 at the moment. So our project statement is to collaborate with diverse communities to design, build, test, and implement wind power technology, utilizing both cultural characteristics of our customers and the technical capabilities of the community environment. Right now our mission was that there was a lack of there was limited integrated and hands-on projects for elementary education, especially in regards to sustainable energy. And in August, we were contacted by a teacher at Allen Elementary who has for a few years had this dream of putting up a wind turbine outside her classroom to help with education and hands-on learning. So she contacted us, and this whole past year we've been designing a small-scale wind turbine to put outside her classroom. And it is built now, and during the design process, we've been making sure that there's an educational application. So we've been going to the classroom and giving workshops and making sure they understand exactly how it works and without too much complication. And now there's several sub-teams, so I'm going to let everyone talk about their own design process.
So the blades team is obviously in charge of designing and manufacturing the blades. Our blades are made of PVC pipe. It's 4-inch diameter PVC pipe that we quartered. So each blade is made out of a quarter of the pipe. They're about 3 feet 2 inches long, which was shorter than our original intended length, but we shortened it to decrease the amount that it would wobble. The rotor that the blades are connected to is made of wood. It's a circle, and each blade is evenly spaced throughout the circle. And we stripped away the wood in between each blade to decrease the amount of wind that would be hitting that area. And then attached to the wooden rotor is a timing belt pulley, which doesn't actually have a timing belt attached to it, but it's used to secure the shaft using a set screw. And the blades team also was in charge of designing the tail, the fin that would direct the wind turbine into the wind. So here you can see this is a rendering of all the parts. The blades this is a very close to our actual blade shape. And the rotor is exactly how it was. You can see there's wood with, that's the timing belt pulley attached to it. And the fin is just made out of aluminum, a simple shape that was designed based on the amount of windswept area. So we, obviously, as we already kind of heard, indoor plumbing PVC isn't UV rated, so it'll turn brittle when exposed to UV radiation. So we're thinking we have two options of new materials to use. It will be either electrical PVC, which is UV rated, or possibly aluminum. But if we use electrical PVC, we will already have the manufacturing process done, which we used for our current blades made out of plumbing PVC. Aluminum blades would require a completely different process, so we're still working that out on which route to take. Additionally, we will have to weatherproof the wooden rotor, most likely using a simple deck seal. And one last small issue is making sure that the that the wind turbine always points into the wind easily, instead of right now it kind of doesn't turn as easily as we would want. So that will either be reducing friction in the joint or increasing the area of the fin. And structure team is next.
All right, so the structure, there were quite a few requirements we had to fulfill. First of all, it needed to be taller than the school, which means it has to be about 15 feet or higher, so that it gets the maximum wind speed hitting it. Also, we want the nacelle, which is the top part of the wind turbine, to be able to rotate 360 degrees, as Mel said, so that it can face the wind and get the optimized wind speed. We also had a space restriction because we are doing it right outside of the classroom of this elementary school. We only had a 12 foot by 12 foot area in which we could put the turbine. We also had to consider safety factors since it is a school environment. We need to make sure that if the turbine, well, first of all, we don't want it to fall, but if it does, that it falls somewhere where it won't injure the building or children. And also we need to do precaution if the turbine becomes electrically charged due to lightning or like an electrical shortage or something, so that it does not shock children as well. We also need to make sure that the battery does not catch fire and burn down the building. So those were the safety issues we had to keep in mind. And also we need to weatherproof all the electrical and transmission components and make sure that the turbine can withstand all the forces put on it by the wind. So this is a design overview for the structure. You can see in about 10 feet up, there's a guy wire connection, and this is where all the force to keep it upright is coming from. So there's 4 wires connected to this component, and those are all connected respectively to spiral anchors in the ground. And then you can see our base platform has these connecting components so that the pole can rotate upward into an upward position. Also on top there's a platform that is connected to a short pole that will slide into the 15-foot pole, and this is where all of the transmission components are going to be kept. And on top of that we have the housing, so that waterproof housing, so that all those components don't get wet. Also we have a housing that will be next to the school for the battery so that it is allowed to ventilate as well as be kept waterproof. We had to do some force analysis on the structure to make sure that all of the thrust force from the wind will be balanced out in the wires. So by calculating the length of all the wires and the height of where it's going to be connected and stuff, we came out with the tension that is necessary to have in each wire and made sure that all of our components were rated for much higher than that. In our action plan from here on out, we have to make sure that all of the safety concerns are fulfilled so that nothing bad happens, as well as we had some extended testing, and we realized that the tension in the guy wires were slacking a little bit, so we need to figure out what we need to do with that to make sure that they're taut. And then we also, as Mal mentioned before, need to make sure that the platform is able to spin more smoothly than it is now, because it is a little gritty and doesn't adjust with the minute wind speeds. And we also need to make sure that our put up and put down procedures can go smoothly and easily. And now to transmission.
Okay, so the functional requirements for our transmission system were to generate 13 volts in order to charge our deep cell battery, to withstand thousands of rotational and vibrational loads, to provide structural support for blades, and to do all this given about 100 RPMs and 1 Newton meter of torque. So our system is composed of a 1/2-inch aluminum shaft, mounted ball bearings, and then our actual transmission system is made up of pulleys, a timing belt, and the pulleys have a 2-to-1 step-up ratio. And then we have the generator, which specs are 24 volts at 300 RPMs. And we have insulation, which, as Structure mentioned earlier, is the nacelle, and we also have on the nacelle like a little awning where the shaft comes out to prevent water from getting in. So we did a fair amount of testing to determine some things for the system. We did some torque testing to make sure our step-up that we chose was accurate. We did this by attaching a mass on a string and wrapping that around the shaft and then taking readings from dropping it. Then we also did some tensioning testing to see what the optimal distance between the pulleys was and how efficient it could be. And then we did misalignment testing to see how much of effect misalignment of either the shaft or the pulleys could have on the efficiency of the system. So coming out of the testing, we confirmed the 2-to-1 step-up. And then for tensioning, we ended up going with generator displacement to do tensioning. And we used those L brackets as seen in the CAD picture right there on either side of the generator in order to move it. For misalignment, we determined that it shouldn't be too much of an issue and that the bearings would account for most of it. For a generator mount, we made a wooden generator base and then put a piece of foam between the generator and the base for damping. And then, as I said, the L brackets are on either side, so that creates more support. And insulation I touched on earlier, but we also have like a foam thing on the shaft to further prevent water from getting in. So our action plan moving forward is to monitor the timing belt for wear or stretching, make sure it is continuing to work, periodically lubricating the bearings, and inspecting the insulation and making sure water doesn't get in. And based on some testing from last week, we also need to kind of like look at the system as a whole because we aren't really getting the voltage that we wanted. So that's that. And then electrical.
Thanks. All right. So our functional requirements for our electrical system is to prevent the battery from overcharging or discharging, to transmit the electricity from the generator to the battery and the battery to the school. We're powering a 500-watt inverter, which then you can plug any device into. And we had to determine the appropriate battery based on our wind speeds and the generator output. So our design overview, this is our charge controller. It prevents overcharging. And the way it works is that once the battery reaches a maximum level of 13.6 volts, it switches to a dummy load. And then we have an extension cord running from our generator and battery to the charge controller and inverter. Our battery is a 12-volt deep cycle marine battery, and we chose a marine battery because you can trickle charge it. And then we have our inverter. Let's see. We did some testing. We ensured that the circuit switches properly, and we set the voltage limits using the potentiometers on the charge controller. The wires, we found the maximum current through each part, and we found the appropriate gauge wires to use. And then the battery, we checked the acid levels to make sure that the battery is still charged. Our action plan is, the issue we found is that we did find on like very windy days that we had the 14 volts needed for our system, but that's not consistent enough. So we're looking into scaling down our battery to maybe an 8-volt battery. We have to install ground wires, and we have to feed the wires into the school, and we're working with the school district's electrician. His name's Rick, and he's a great help to us. And we have to build a second circuit to stop the battery from drawing power once it reaches a specific limit, and that would be placed in between the battery and the school. And that will prevent the battery from discharging below 80%.
All right, so typically we're an international project, but this year we've been working locally. And over spring break, we initiated our new international project that's located in Guatemala and El Salvador. Right now we're just at gate 1, we're just starting, but it's going to be a collaborative, a collaboration between us and 10 young Guatemalan and El Salvadors. And yeah, we're going to be focused on designing turbines for certain communities, and as well as like a big educational and local empowerment movement. And so that is our presentation, and thank you. And do you have any questions?
Yeah.
So I guess as far as the battery, if you were to change it to an 8-volt battery, what sort of limitations would you have with the devices it could power?
We haven't, so we haven't really looked into it, just because that's sort of a recent development, to change the battery
Okay,
because we just did testing, over spring break
okay.
based on our wind speeds.
Okay, so soon you'll learn more about different battery options and how that might power different devices and stuff.
Yeah, but I think that it's still gonna be compatible with the inverter,
Okay.
which would then we'd still be able to plug anything into.
Okay. I guess one other with the blades, I felt that at least in comparison to the other components of the presentation, I felt that there's just a few things missing in that, and maybe I missed this, but was there a slide about the functional requirements for the blades?
No, there wasn't.
Okay.
I guess we had the slides of past presentations, and the original intended length was going to be 4 feet. I don't know, Brandon, do you remember what the calculation was to find that?
The idea was they had to supply a given amount of torque based on the wind swept area and wind swept radius. We originally started at a 4-foot length. Shortening it down to 3.2 for stability reasons. So kind of the reason we were a bit hesitant about that is because we were really designing around other aspects of what we needed. The thing about Open Wind is that we sort of have to integrate our requirements with the requirements of each other group. And I think that with the other group sort of representing that, and given what we can, like, we sort of have to operate around what they need. Like if you're building from like a battery up, then you're going to be requiring like a certain amount of torque in order to go to transmission to go to electrical. I just thought I was hoping that would be a better integrated presentation.
Okay. So